Well, ladies and gents, it is that time that you have all been waiting for. As I say, it's an honour, it's a privilege to welcome to the stage at Kimbolton Reverend Ron Lancaster. He came to teach at Kimbolton in the mid-1960s, taught chemistry, was the school chaplain, divinity and psychology, I believe, as well, in the mix, through to the mid-1980s when he retired to then start a career or continue his career of running Kimbolton Fireworks. Ladies and gentlemen, it's our great privilege, Reverend Ron Lancaster.
Thank you very much for asking me to come and talk about my favourite hobby. It's been going on for quite a long time, and really at the beginning I thought I ought to just say just a few words about how I came to be involved. I grew up in Huddersfield, which was the centre of the firework industry in the north. And we had 2 or 3 factories there, and as a teenager during the war, we used to sometimes go and watch what was going on when they were testing military pyrotechnics during that time. The biggest fun was to go up the moor towards Manchester, and Standard Fireworks there every day set off several hundred parachute flares, testing the ones that had been made the day before. This was a square yard of silk, which was well worth having in wartime, at least my mother thought so. And so you went suitably dressed, really. Mac, Wellingtons, it was heather, and you had somewhere hidden a long clothes prop, because as the parachute sort of came down, as the flare had gone out, you caught the parachute before some other little monster who hadn't got one as long as yours. So this was really the fun, but the school colleague of mine who claimed that this started him in his running career, a man called Derek Ibbotson, who was one of those early 4-minute milers, I was the one who used to go and find the flares that hadn't ignited and get it before the men from the factory got it. So this was really how my interest in fireworks began. And after obviously a few years having a break, then I came back to it later on in life. But the main thing was that I knew quite a lot of people who knew how to make fireworks. And so we made our own rockets and I suppose a few sort of bangs and things like that. But basically, we were more interested in trying to get the burning speed of our homemade gunpowder to work properly. And in order to do that, we had to make our own charcoal, which we cooked in treacle tins, which we buried in the fire, because to make good charcoal, you have to heat it in the absence of air. So that was the beginning there. Now, there's a lot more I could say, but I want to pass on very quickly and come to 1963. Because when I went to the university, I went there as a chemist, but on the other hand, I decided to be ordained. And so when I left university and the army, I went back to the West Riding to serve 2 curacies, each of 3 years. And at the end of that time, I applied to an advert, which was for a chaplain at Kimbolton School. Now, I have to be fair and say that I hadn't heard of Kimbolton. I didn't, even not being a historian, know about Catherine of Aragon all that much. And so basically, I applied for the job and came here. Dear man Cyril Lewis, who was the headmaster, obviously knew from my curriculum vitae that I had quite a connection with the firework industry. So when we'd agreed that I would teach divinity and some chemistry, he said, "Is there anything you'd like to ask me?" And I said, "Is there anywhere I can build a firework laboratory?" And I wondered if he would fall off his seat. Just imagine what a normal reaction. I don't know what Mr. Belbin would do if you got a new member of staff who said, "Is there anywhere I can build a firework factory?" So he said, without batting an eyelid, he said, "There's a walled garden quite near the house where you're going to live, and if that's suitable, you can have that." So that was 1963 September, and we had the thing in place by 1964. And although it's illegal to have alcohol in explosive premises, the bachelor staff at that time had a little cocktail party in the new buildings just to start them off. So I don't want to say any more about that really, because this is a lot of things I'm going to try and say today about fireworks and explosives primarily. So let's take a look, for example, I don't normally do this, but because fireworks are part of Kimbolton these days, I thought that I'd spend the first part of this talk talking about the different kinds of fireworks that we have and what they look like, and perhaps explain them before I get on to some of the details of how they work and what happens when you ignite them. This little collection here, all these are dummies except one thing there, and these are the sort of fireworks that you, not in school here, but parents would have bought in the shops probably 20 or 30 years ago. And look how attractive they were in their own way. There's one that we used to make at Kimbolton Fireworks with our label on it. But here you've got Brock's, you've got Lion, you've got Standard, and so on, or a big modern cone from China. So those were the sort of things that were familiar. And you'll notice they were ignited with touch paper. This now doesn't exist because we can't guarantee the burning time. And so nowadays we have a special fuse which, alas, is made in China, and it does at least give you an accurate burning time. So those then are the original shop fireworks. But now let's turn and look at some of the bigger ones, which are more of a concern of ours at Kimbolton here. So I have a small script here because I'm getting to the age now when I sometimes get things in the wrong order. A friend of mine said quite recently, I'm just going out now on the telephone and I'm going to polish my shoes and powder my nose, but I might get it the other way around. And so I'm going to start then with rockets, and obviously it's something that everybody's familiar with, but maybe they're not too familiar with the actual reason we call them rockets, and the truth of the matter is we don't know. But that's the sort of thing, we think it's an Italian expression primarily, but that is the sort of thing that you're going to buy in the shops. And what really is happening is that the whole of the inside of this tube here is hollow, because all the powder has all been pressed around a spindle which is withdrawn, and that means that the whole of that tube is immediately lit, and there's so much gas coming out of here that it pushes the rocket up into the air. If you go then a bit bigger to the sort of things that we use at Kimbolton in our firework displays, you're coming to something more like this. And this is a different kind of rocket, more like the sort of things you find in the military, where here you've got a compressed gunpowder charge with only a very small hole in the bottom. So this is neat gunpowder. These do not look as good when they're going in the air as these, which have a very nice golden tail. But on the other hand, these are very efficient in the way that they're made, and they don't go wrong very easily. And of course, we sell them in a plastic tube in order to fire them easily in your garden. The biggest rockets that were made until about I would think 50, 60, would be a rocket like this. And you could actually buy them. I remember the price as a schoolboy was 5 shillings, which was a lot of money in those days. But you can see that's a very big rocket. And this big swelled head was primarily for carrying a parachute or some other object that was quite large, which was going to do something high in the air. This is a dummy, and we made it up really for the Christmas tree festival in the parish church. But that's exactly what it looked like, and the same stuff. but also ought to tell you that here's another rocket, and this is live as it happens, and this is a ship's distress rocket. Because what happened, or was very common in past times, when it was necessary to get a cable or a rope over a ship in distress, you had to fire these sort of rockets. And so this here was connected to a specially, I don't know how to describe it. Imagine that you are firing a rocket at great speed and it's got to unravel a rope, a thin rope that's coming out of a contraption. Imagine what the contrivance is like to stop it getting all mucked up as it's coming out. And so the contraption they used to make in order to dispense the thin cord that goes first and then leads to the thick cord is really complex. The new ones that I've seen in recent times are a lot more efficient, of course, but you can see how they were made in the old days. So the rocket motor, it's all rocket motor. That's a very big rocket motor, and that would make a lot of sparks and a lot of noise. So enough said about rockets. The next form of next form of firework that you're probably familiar with is a Roman candle, and this is a universal word, and I think it's been invented probably, or came about from the English, because you see, firework terminology is pretty universal, and it seems to be either English or perhaps bits of Italian. And so Roman candle is the most common word. It doesn't matter whether you go to Germany, where it's Römische Lichter, or to Italy, Candelo Romano, or whatever, or Spain, or whatever it is. It's a very universal sort of word. And I have here two for you to look at. And so this one is the sort of Roman candle you buy in the shop. And what is it doing? Well, you've got maybe 3 pellets in here, which we call stars, which are coloured lights that are going to come out and go perhaps the height of this building, a bit more, and this size. And in between each star, there is a gunpowder charge to lift it, and a delay. The delay is just burning, fizzing, doing something or other. And so that would be the sort of Roman candle you might be familiar with in that group. But here, we only make, at Kimbolton, we only make Roman candles of 30 millimeters, or even bigger, at as much as 60 millimeters. So you can see that in this case, it's same thing, we've got 8 comets in here, and they'll all fire together, and they'll throw the set of comets out every 3 seconds. And so you get this continuity, and probably something like this might burn half a minute and give you quite a good display of colour or whatever it might be. So now we come to the most, I suppose, spectacular kind of firework, which are called shells. They are called shells simply because they are fired out of a mortar tube. So the mortar tubes used to be made of iron, or perhaps these days they're made of fiberglass or paper. And so here's the little one, you see, a little titchy one, which we used to sell years ago, before they were banned. And, and so you can see that if somebody lights that, and this comes out and goes 200 feet in the air, and they're sort of looking at it, it's not very good, really. So they can be dangerous. It's a shame they were banned, because used sensibly, they're fine. So what you've got here is gunpowder, and then you've got a ball of paper here with a fuse, and it's full of coloured stars. So that when you drop it in the tube, this fuse takes it right to the bottom, the ball goes in the air. Fuse is about 2.5 seconds, you'll see that shortly, and then it bursts in the air. A round shell has its advantages, because if you have the burst charge in the middle, all the contents are spread all in all directions. And we can make patterns with a shell of this type. For instance, with a shell of this size, we could make a pattern in the air of a letter, like A, or whatever, or a circle, or whatever you want. And so they come in all sizes and shapes. So that's the next size up. Well, it's not the next size up, but that similar type. Or we have cylinders, because you may want to take up into the air fireworks which are long and narrow, so we might have a lot of them in there, and they burst easily. Or something that we used to specialize in Kimbolton, making this type of shell, where it will go in quite high in the air, quite a big bang when it goes up, and it will probably do 1 break, 2 breaks, and then 3 breaks here, or at the bottom here, maybe a big bang of some sort. These are getting very expensive to make, and they're handmade, and they're made with paper and string. And so these, again, I'm sorry to say, are becoming more of a rarity simply because of the price, which is very, very sad, but that's how it is. But that's shells, and just to sort of show you the sort of sizes that it goes to, here's another big one, which is, as you can see, which is 250 millimeters, and so that would be really quite a big spread in the air. The Japanese have the reputation of making them 36 inches in diameter. It takes them about 6 months to make one, and I've never dared ask them what the price is. So that's how it is. This is actually a dummy, full of sand actually, but it is, as you can see, really a big thing and very spectacular and very noisy when it goes off. So that's shells. We're coming along nicely. Now we've got wheels, and this again is something that we make quite specially at Kimbolton, but they are in fact really getting very expensive, and you can probably see why. So obviously from China, if you want a simple wheel, you can put a nail through here and put it on a post and it'll spin round. It's obviously quite pretty and it's really quite cheap. On the other hand, we make these at Kimbolton, and you can see why they're expensive, because you've got a 6-inch nail here which goes in the post, and of course it turns around. It burns gold to start with. Both these two are turning at the same time. Then it turns silver, and here you've got 2 colored lights which give you a ring of fire in the center. But you can imagine the cost of timber, or even turning a boss like that, doesn't make them cheap. But on the other hand, there's a very difference in quality and performance, as you can imagine, between that and between that. There are 2 other things that I'd just like to mention as firework types, as we say. So let's take this one first. When we want to make fire pictures, which are seen, you know, at this sort of level, we have to do it like they do with lights at Blackpool. You have to design a very simple drawing, and then you have to, it mustn't be too fussy, and then you have to put individual lights along it. They're about the size of a cigarette, they burn a minute, and then we can connect them here with instantaneous fuse. So you can light the whole lot together in one go. They're called lancers because they're long and thin. And really, it was very typical of the fireworks of the period up to the last war. Wherever you went to see a firework display, there would always be some of this stuff. It may well have been, you know, pictures of, or maybe a portrait of the Queen was very common at the end of a firework display before the war, or it would say good night. I remember talking to a boy after a firework display, he was quite young, and I said, what did you like best in that firework display? And he said, that thing that said good night. From our point of view, it's probably the most boring thing we do, but that's another matter. But it's all in the eye of the beholder, obviously. So that's lance work, and then the present century and in recent years, we've now come to these objects which are Chinese, which when they first came were round and about that high and just about the size of a cake. So they're now almost entirely called cakes. They have one ignition and it will run around here and it will perform for quite a long time, and it's the fuse that's running between the tubes that does it. So I've brought you a spent one so you can see what it looks like inside, so that you've got a whole series of tubes and they're all connected by a fuse at the bottom here, and they can be made to do all sorts of things. They can either go one at a time in lines like that, or they can go that way, or they can do all sorts of tricks with the fuse in there. And they're very common now and really becoming very much the easiest way of buying a biggish firework. People say, oh, I just want one big firework for New Year's Eve. And so you can see how these have become very popular. So those are the various types of fireworks that we use and make, and I want to now see if we can have a little bit of history. If we could have a slide that's coming up of how the firework trade has developed, and we'll see what we've got. Okay, yeah. Yeah, that one, yeah.
It's on there for them, they can see it.
Oh, they can see it. Oh, right, okay. Sorry, I can't see that. So, clearly, you can see how gunpowder probably was in some kind of form that we're familiar with by about 800. And then it was probably brought to Europe by Arabs. We are pretty sure that Roger Bacon got his information from Arabs, but there were no things like fireworks until about 1520 or whatever it is. So that is really quite significant, really. It's all comparatively recent in history is the use of gunpowder. Now, the Chinese were not looking for gunpowder. They didn't know what it was. They were looking for, if you like, the elixir of life, this magic substance which was going to make you better, stronger, whatever. And they probably were looking mostly probably for common salt or whatever, but they in fact would be collecting nitrates, probably from the deterioration of animal matter and so on. And so that is in fact how they started. They mixed these chemicals they'd found with carbon of some kind and, strangely enough, honey. And they found that it caught fire and, of course, burned their faces and caused quite a lot of trouble to them. So as you go on there, fireworks didn't really come about until really something like the 17th century. And so I'm not going to dwell on these, but you can see how you're not really getting until 1742 until you begin to see clearly that there were fireworks being made for Handel's firework music. And of course, that firework display was a bit of a fiasco, as you perhaps have read. But the most important thing there is 1800 and the development of the chemical potassium chlorate by Berthollet, because that did change the whole composition of fireworks. So if we move on now to the next little bit, you can see how in Japan they came up with a very special kind of firework, which is really the basis of a lot of fireworks that are coming from the Far East today. But all the rest of it there starts from 1983, where you can see how, unfortunately, the regulation of fireworks has become ever more complicated, and we now have a situation in the EEC where they are saying that all fireworks must be completely regulated by 2017, and that means that we're going to have quality control for everything we make. We're going to have to pay fees to the people who administer this. It's going to put the price up, and there are lots of fireworks we shall not make anymore because it won't be worth paying the fees to have them done. If you're only making a few hundred of something a year, there's no point in paying £1,000 to have an EC mark on it when really you don't sell enough to make it worthwhile. It probably started off as a good thing. It's developed into a bad thing, and we feel it's got so bad now that we don't know what to do about it, which is one of those unfortunate things. I'll move on now, while we're looking at these very quickly, to types of explosives, because these are quite fundamental to what I'm going to try and say to you in a few minutes. So, Alistair, if we could have types of explosives. Well, first of all then, we've got three kinds of explosives. Those things, which we call 1-1, which just go bang. There's no hanging about. It's gone, just like that, in less than a second. And so what is really happening is that these solid substances, certainly as far as I'm concerned, are solids which suddenly turn into gas. And if they're in a container or something which holds the gas, then of course it blows the container to bits and you create an explosion. So that is what a high explosive is. Then you have propellants over on the right there, which don't usually go bang, but they burn so fast that really they're over in 1 or 2 seconds. So the most familiar one, perhaps these days, are airbags. Hope you don't have to experience them. They can't be very nice, but this bag of gas suddenly confronts you and probably stops you getting whiplash or whatever it might be. And so that's what a propellant is, but rockets, of course, are propellants. Now it brings us to pyrotechnics, which usually are things that take place at a speed that you can watch the reaction taking place. It may only be seconds. Your rocket may only burn 4 seconds. It seems longer to you in the dark watching it, but you can see it taking place. You're going to see quite a lot of them taking place shortly. But that's what a pyrotechnic actually is. And so it produces flames, usually, not always. Some reactions are almost invisible, and delays and things like that. But the important thing is that not only does it produce flame and gas, but it produces solid residues as well. Now, these solid residues are quite crucial, really, to the explosive nature of pyrotechnics. In other words, you are having only a proportion of gas. Your high explosive is all gas and goes bang in that kind of way. So that gives you an idea. We'll have a rest now with the overhead there while we take a look now at the mechanism, really, of explosives and gunpowder. Now, what in fact happened was that as the gunpowder developed, perhaps, Alistair, just to be awkward, I will look at the gunpowder one now. It's easier. So as the gunpowder has been developing over the years, it started off with the Chinese, you see, down there with sort of proportions which are quite different from how they end up there. You look at the right side of the chart, and you can see that the bulk of gunpowder is potassium nitrate, and it's about 75%. Then the next sizable constituent is charcoal, which is about 15%, and then sulfur is 10%. But you can see how it's varied over the years. Now, what is important about it is that it's not the exact percentage that matters, it's the way that's been combined together. And so, as gunpowder has progressed, it's got better, it's got more efficient, because what they were trying to do was to make better production of gas faster, because gunpowder has been used really as a propellant or as an explosive. And I would say that it got to its best probably in the Napoleonic Wars, when they got to the stage where they were asking themselves, you've got a lump of something like gunpowder, and it's going to burn to produce gas. Now, if you think about it, as it burns, the surface area is getting smaller, and the amount of gas it's producing is getting smaller, when what you really want is the whole lot to go together. Bang. So what they did was to compress the gunpowder into prismatic shapes with a hole through the middle. And they found that was the best shape for gunpowder, lumps of it in bags, that shape. So it's burning from the inside and from the outside. Maximum burning speed is what you've got. And probably that was at the best time in the production of gunpowder. And in the days when it was being used, of course, it was not too easy to carry it around because the cannons were extremely heavy. The roads were appalling, and so in warfare, most of it took place at sea. And that's why on the ships, really, you had cannons and people holding them, as you know. There are lots of expressions you're probably familiar with. And the gunpowder was kept in the bottom of the ship in the bags. And you had young lads, some of them your age, whose job it was to run down, bring the gunpowder bags up, and give them to the men to load into the cannons. Unfortunately, the ships were all made of wood. So, of course, when the ship got hit, a lot of the damage was from splintered wood. There was blood everywhere, blood all over the steps of the people who were having to fetch the stuff up from the bottom, and they had to put sand on that to stop them slipping on it. Nasty business, really. But it's the only way they could carry out warfare, by carrying the cannons around in that kind of way by sea. And gradually, of course, it started being used in other forms of musketry and all the rest of it. But basically, that was what was happening. And the gunpowder probably was at its best about that time. But unfortunately, just when they were getting it as they wanted it, an Italian called Sobrero came along, and he discovered nitroglycerin. Now, the trouble with nitroglycerin is that it's very sensitive to shock and friction. You know, you can't drop nitroglycerin on the floor, it explodes. But it was goodbye to black powder as we know it. It was the first high explosive that was discovered. Sobrero was so frightened of it that he didn't use it. So it was Alfred Nobel who came along and phlegmatized it with material to make dynamite. Nobel made his fortune, and Sobrero was so angry that, in fact, Nobel had to pay him a pension right until the end of his life. So basically, that's when everything changed and high explosives came into being. There's a story about the crooks who used to want to blow the locks. And gunpowder is very messy to handle, bulky, and sort of the gunpowder plot could have been an awful mess, really. And gunpowder wasn't as good as some people reckon it was. I don't know. But basically, bulky and nasty and heavy. So nitroglycerin was wonderful. You could pour that into the lock, put a detonator in there, blow it very easily. But it's very sensitive. So I'm told that the crooks used to carry the nitroglycerin around in bottles, which they slung from their belts. And I just have visions, you know, of one meeting another and giving them a smack on the backside and blowing them up. But that's another matter. But that was goodbye to black powder and the development of modern gunpowder as we know it, sorry, modern explosives as we know it. Let me give you an example or two now of the way, what gunpowder is like when we burn it and the sort of things that it does. Just get rid of that. In fact, Alistair, if you don't mind, we'll get rid of these bits on the bench as well. If you don't mind, thanks. So let's take a mixture of potassium nitrate, sulfur and charcoal in the quantities that is normal, just as you might be able to buy them or get them from any source whatsoever. And these are not well made. They are just mixed together, these powders. And when we burn it, you'll see that you would hardly describe it as gunpowder. So here we go. It doesn't light all that easily, but you'll notice that it's messy, it's bubbly, there's a lot of residue there, and it's left really quite a deposit on the plate. So in no sense of the word could you call it gunpowder, but it is gunpowder in its chemistry. So I'll push that out of the way. So let's take another one now. And burning them in this way tells you a good deal about these powders. So let's now take the same stuff and let's put it through a sieve which has 120 wires to the inch each way. We've got 120 mesh sieve. Now, if you were to measure the aperture between those wires, that is 125th of 1,000 millimeters. Very fine sieve, about like fine baker's flour. So the same stuff, light it this time, and you'll see it's changed its character straight away. So obviously the fineness of the material is really quite crucial in this particular case. And that's not gunpowder, because we just mixed it together. So this time, let's put the chemicals into a mill, and this is an edge runner mill where you've got two big wheels rolling around on a pan and gradually incorporating the charcoal and the gunpowder and the sulfur. And after, say, a couple of hours milling of that, then you end up with a powder that looks like the last one, but on the other hand, the ignition you might expect to be a bit faster. And so really what you've got there is a slight difference in the pattern again. And I'm just a little disappointed because the Bunsen burner usually tells you something else, but the next one might. So let's say now then we're going to make this powder into the kind of powder that will do a piece of work, like lifting a shell or a Roman candle or whatever it might be. And so what they do is they compress the powder into an absolutely solid rock cake, and then they break it down into grains so that it ends up looking like black sugar. So here we have the gunpowder grains. We have them all sizes from about, well, 1 millimeter up to about 7 millimeters. And so here we go. When we light this, it may not be all that quicker than that, but it is quick, and it's put the Bunsen burner out. Now, that's quite significant, because you see, what is happening is that you've got an explosive front here, you've got an immediate concentration of gas here, and what it's done is push the Bunsen burner out because of what's happening there. Other explosives are much worse than that. That's comparatively easygoing stuff. So look at our 4 plates now, and you see the original terrible one here with all that residue left behind. Look how that one hasn't done a lot more than stain the plate, what you might call a gunpowder burn. And then look at this one, where the grains have all pushed each other out of the way. And this gives you a very clear idea of the burning characteristics, if you like, of those 4 powders, which are absolutely chemically identical. And so you can see that there is a lot to learn, really, from burning chemicals on the ground, if you like, or mixtures, and watching them, even smelling what they smell like. Now, if we were to mix gunpowder with other things, we make some of the most ordinary fireworks that we have. So, for example, we could have, because these all look alike, I'm not going to actually tell you what they're going to do until they've done it. So let's have a look then and burn 1 or 2 of these, and we'll get a clue of what's in. But it's gunpowder mixed with other things. So I imagine that's probably charcoal and probably a bit of metal powder. You can see the gold of the charcoal, and there's a little bit of magnesium aluminium alloy in there to give it that effect. Let's now try this one. That's got titanium mixed in with it. So titanium is the newest metal to be available for fireworks. It used to be very expensive, but it gives the most beautiful silver sparks. And of course, it doesn't corrode in the same way that other things do. Let's take another one. And so this time, we've got what we call a flitter, which is aluminium again in a different form. It's not as fine, and it forms those kind of what you can only call flittery effects. And this time, you'll see that it's flittery again, but different. So that we call a glitter, and that's aluminium again. A lot of these aluminiums give you different effects, but there's antimony in there as well, which gives it that kind of effect. Here's another one, which I'm going to be just a bit more wary with, and because it's got a coat on the outside of it, a material, and what happens is that it sometimes jumps sideways, which isn't too convenient. In fact, I've got 2 of them coming up, so I'll be a bit more cautious. Because you've got to be very cautious, you don't get the whole box on fire, but I've had it happen once. So here we go now with this one. Now, this is aluminium with a goodly amount of oxygen in the composition, making it burn very bright, you see. So the more oxygen there, the more the aluminium burns more brightly, obviously. And then there's this one, which we make quite a lot of, and it's quite curious. I'm jumping slightly back, because this interesting effect, which probably, in fairness, the Chinese came up with in more recent times, that crackle is made by mixing aluminium and magnesium aluminium alloy with an oxide of bismuth or even lead or something like that. Lead makes the best results, but of course lead isn't as popular as you can imagine. But there we are. So that's the kind of effects that you get. Aluminium is very interesting when it burns, you see, with gunpowder, because at low temperatures it burns silvery gold, but as you notice at high temperatures, with lots of oxygen, it burns really very, very bright indeed. Now, the earliest fireworks were just rockets and a few squibs and bangers, and the colours were really very primitive indeed, very poor reds and very poor greens and mostly white. And that was because there was no potassium chlorate. Now you saw there that Berthollet discovered it in 1786, and Berthollet obviously brought a whole new background to the firework industry. And potassium chlorate created a lot of problems, because the firework industry in the early 19th century was mostly in domestic premises. Whole streets in London used to blow up as they made the new colours with potassium chlorate and dried the stars in front of an open fire. And there were lots and lots of problems, and all of that led to the explosives acts when they came about. But I wanted to show you now a little bit about gunpowder, its general uses in other kinds of ways. So let's take another little bit of our fuse. I'm going to use 2 bits of it this time. We're going to just burn it as it is in the open, and you can see that if you make gunpowder into a paste with starch or something like that, you can then put cord through the middle of it and make it into this stuff we call quick match. So you see it burns at a fairly steady rate. It's fairly predictable. If, on the other hand, we put it in a tube, obviously you're increasing the pressure, and to some extent you're increasing the temperature. So the question is, how long does a piece of that take to actually get through there? And you'll see for yourself. I'll put it into this clamp. The problem, of course, as you realize with this lecture, you're getting more and more smoky as you go along, but there we are. So how long does it take to get through there? Well, not long at all. And so basically, you can see how, in fact, the firework industry lights lots and lots of little fireworks all together with match made like that. So we're going to do some other things with it now, just to try and illustrate how these things work. So if we were to control the gunpowder and put it into, make it into a manufactured fuse, then it will behave really quite well and very reasonably. So let's take 2 examples of that to start with. Sorry it's a bit slow, but I just have to be careful. Slow as the box. So let's first of all now take a tube like this, which is 6 millimeters in diameter, and it contains about 25 millimeters of gunpowder. Now, because it's in an open tube, and because it's been well compressed, it is the fuse of a star shell, we know that it will burn at a steady speed, and we know that it will burn about 2.5 seconds. Might be better off moving to this end, really. And 2.5 seconds is about its burning time. But notice, because it's a very powerful, extremely powerful gunpowder, you notice the height of the flame, you see. So that's all you need to get a shell 200 or 300 feet in the air, because it's gone and it's away. So gunpowder in its early days created a lot of problems, and particularly for the miners, particularly in Cornwall. And there was a man called Thomas Bickford who decided that it was no good using the old method of setting off gunpowder charges in the mines, which was to fill a quill with gunpowder. And then, of course, you light the quill, and it's wet in there, damp, and then suddenly, of course, you get a hang fire. It doesn't go off, and then the miners go back, and, of course, that's the time it decides it will go off. So Bickford invented a machine whereby he could produce a fuse which was a slightly slower gunpowder going through a system like this with cotton wicks going down inside it as well, and then he covered it in pitch on the outside. Nowadays, of course, it's covered in plastic, as you can well imagine. But you can see how steady it is. Again, you can predict always what the time is going to be. And so Bickford fuse is extremely useful for all of us who are making fireworks and so on. So they are, in fact, very easy ways of using gunpowder. Now I'm going to show you next then, if Alistair's here, come and help me, Alistair, will you? We're now going to see what happens when we ignite these in a drum. And because here's a little collection of Chinese crackers, and they are going to, we're going to put them in here, and there's not much gunpowder in there, but if you lift, you put, Alistair's going to ready to bang the lid on. But,
get the lid off.
all right. Leave the lid loose.
Leave it loose.
Yeah. Okay. Are you ready? You get half on. You get the lid half on. Give me an opportunity to get it in.
So take that one away.
Yes, very good. So, let me say, of course, that gunpowder, it's an interesting substance, you see, because it's very easy to handle. You can knock it about pretty well, and it doesn't explode. I mean, you've got to be careful, but I mean, you could put it on the wall and hit it with a hammer, and it wouldn't do anything at all. It's pretty good, unless, of course, you've got metal filings there that'll create a spark. It's the spark that lights the gunpowder. And so in the early days, when gunpowder was being made in huge quantities and was really being transported really on pretty awful conditions, I have to say, barrels were leaking and powder was on the floor and so on. So really, if you were to light gunpowder, you get a puff, and that's it. And you light more and it just goes the same way. But there comes a stage, there is a quantity you might come to when it will not just light, it will detonate. And so quite a lot of gunpowder is a serious matter. And so just wanted to tell you about October the 1st in 1864 at Erith, south down the river from London. Because they used to keep gunpowder on barges on the Thames, just about 20 yards off the Thames itself. And there were two barges there which had on the barge 52 tons of gunpowder. And on that October the 1st, 1864, the whole lot went bang. Nobody knows, of course, because nobody survived to tell them. But it destroyed all the houses along the riverside, and really the debris was quite a long distance. 52 tons is quite a lot. And what amused me about the story, it's well documented. Remember that in middle of the 1800s, it was very popular in Victorian houses to keep caged birds. And it said that all the canaries lay in the bottom of their cages at the end of the bang, and the parrots refused to talk and lay there for hours. And it was an interesting comment on something that happened at the time. We were talking earlier on about the discovery of chlorates by Berthollet, and so we're moving now to really what happens with perchlorates. Perchlorates we use because, for those of you who are chemists, you've got chlorine there with 4 pairs of shared pairs, and basically potassium chlorate has a spare pair there, and basically we think perchlorate is more stable, but it's not really as good as chlorate for making fireworks. But perchlorates with metal powders are extremely brisant. It's a French word really meaning extremely active, and will create these waves from their ignition. And so, just to give you an example of this, I think perhaps we will, could I have the drum again, Alistair? I've brought you a little tube here with just a bit of perchlorate and metal in it. And we'll leave the lid off. Oops, a daisy. But in here, this little tube here with this electric ignition, there is 0.05 of a gram. Now see how little that is? Not very much. Not much at all. But you'll notice that it's a different kind of noise as well. Let's move it a bit that way. It's sharper than the gunpowder bangs. You see, it's quite different. And but think of the quantity. So small. It's a pinch, if you like, and nothing much more than that. Let's go on really now to look at other things, which really is moving on to this later development of chemistry, because the 19th century was a great time of discovery of what we now know as modern explosives and things like that. So we had two chemicals which really are of interest at this stage to talk about. One is trinitrophenol, and the other is trinitrotoluene. Trinitrophenol is usually called picric acid, and it's not very nice stuff to handle. The word picria in Greek means bitterness, and anybody who handles picric acid or picrates knows it straight away. Somehow it gets in the atmosphere and you can taste it. It's really bitter. And it's intensely yellow and was used as a dye, and it makes your skin yellow if you handle it all the time. In World War I, they actually melted the stuff and poured it into the bombs and as a solid mass. It melts at 122 degrees and is really quite reasonable to handle and isn't particularly dangerous as it stands as picric acid. Now its salts, potassium picrate or lead picrate, a very different story altogether. And I just wanted to say a little bit about it before I come on to tell you why I'm talking about this bit of firework chemistry. You see, the bombs in the First World War were not all that sensitive. You tell that picric acid isn't all that sensitive. If they are traveling at 3,000 feet a second, these bombs full of that stuff, and sometimes the detonator didn't act and they came down and landed on the floor and still didn't explode, you can't really say that picric acid is all that sensitive. But about 1970, somebody discovered 100 grams in a school laboratory in America, in the South, and the whole town went absolutely bananas. They closed the school, they moved all the people in the houses round about, and they started going to all the schools, collecting all the picric acid, which was used sometimes in ordinary chemistry, and created really quite a stir. And really, that's a very sad story, because it tells you something, that nobody uses picric acid very much anymore, They don't really understand anything about its explosive properties because all the people who did have passed on. And it just shows you how you get this health and safety scarism which sometimes takes place, which we call safety faking. And there's a lot of it goes on. But I'm telling you that really because it was very interesting because of the American reaction to it. Now, potassium picrate, somebody discovered that it makes a noise when you put it into a firework. And I'll attempt to show you just a little tiny bit of what it does. And so that was very popular for quite a long time in fireworks. But lead picrate is also quite dangerous because there's a story in the history books of a factory that had barrels of picric acid stored for a long time by lead pipes, water pipes, and the picric acid was getting on the lead pipes and it was gradually converting it into lead picrate. Somebody went and moved the barrel, exploded the lead picrate, which is very sensitive to being, impact or friction, and blew the whole place up, destroyed everything. So this is, again, knowledge is very important in this kind of thing. So let me show you an example now, I hope it behaves itself, of a picric acid whistle. And you'll notice that it's quite short because if I used a lot of it, you'd all be tasting it. And that's not very good. So here we go. It helps to put it in the tube the right way up. Often happens with fireworks, doesn't it? So here we go. Oh, it'll go. You see how it produces this thick black smoke and this tiny little whistle, which is quite different from what we use now. All these whistling fireworks that you hear are actually chemicals that are burning. And what's really happening is that you've got a kind of reaction taking place at the bottom of a tube where the burning's taking place. And this, in the molten state, it is in fact giving a kind of strobotic motion, really, stopping and starting. And so basically, if I can find some, we'll take two examples of this. And here's the first one. But all the chemicals that are used are related. So if you think of the structure, for those of you who are chemists, of potassium picrate, picric acid, move over to benzoates or salicylates, and they will do the same thing. And the Chinese, who have been using potassium hydrogen terephthalate for making tires, also started using it for making whistles. So here we go. So next example then. Sorry it's a bit slow having to do these bits of maneuvering. So here's number one. Now it's interesting because what's happening is that most of that reaction is taking at the bottom of this tube, and this empty tube here is acting as a resonator like an organ pipe. You know, when you have an organ pipe performing, you've got a column of air which is vibrating, but it's been caused at the bottom of the tube, and the same here. And you can in fact make long tubes and different sounds. But I can assure you, we have tried on occasions to play a tune with it, and you can't fine-tune it. So here we go. Now, a Turkish pharmacist, who I've known for many years, played around with these things in a very big way. And he changed these so that he makes them burn so quickly that they don't really know what to do with themselves. And it really is quite a different noise. So you can see that there is quite a difference there. And that's because you've speeded up the burning speed so fast by making a hollow down the middle of the composition that it doesn't know whether to whistle or to bang. That's really what's going on there. So that really is quite a unique technique. Very good for scaring birds in airports. Very handy. It works well. So I hope that explains the function of whistles. I would also, at this stage, mention the fact that catalysts play quite a reaction in fireworks. So again, for the chemists here, I'm sure you've been told many, many times now that a chemical reaction that is taking place in one-way direction, and in a firework it's going from solid to liquid at the burning phase to gas, and then sometimes it becomes incandescent and produces a flame. So here you've got the solid, you have the liquid phase where the reaction is taking place, and then you have the gas coming off. So good piece of chemistry really for a change of state, solid, liquid, gas. But I'm sure in a school like this, students know that you have a condition which takes place where you don't go through the liquid phase, and that's called sublimation. And so sublimation is used in fireworks quite regularly for making smoke. So what we're doing is we're finding a simple heating mixture and letting it smolder, and then it will sublime the insecticide, if that's what you want to do with it, or make the smoke for signaling purposes with the military. So here we go. Here's an example, you see, of such a reaction taking place here. So there's no flame, so all it's doing really is subliming that particular organic chemical which is there. And it's quite effective. Those particular pellets are used for putting into pipes to make sure there's an airflow through them and they're not blocked. We had starlings on our chimney last summer, and they were being rather a nuisance. So I put one of those in the grate, a big one, and ran up the garden to watch and see what happened. And it was fascinating. They stood there looking at each other, looking down the chimney and going, whoo, whoo, like this. And then they all cleared off and we've never seen them again. So that's what happens then with that one. Or you can, of course, use organic dyes, which is very commonplace in military signals and that sort of thing. That particular one, if it gets your way, will smell of toffee, because the fuel that is burning there is in fact sucrose and sugar, and so basically you get that kind of toffee smell coming from it, though not all that interesting really. So I want to move on now, coming rather onto the time I've stopped. I want to talk about colour. So colour is quite a different division of fireworks from black powder. And so what in fact we're doing is getting a chemical that will provide the oxygen, an oxidizing agent, in this case potassium chlorate. We then add a fuel that will do the burning. And then we add preferably an insoluble chemical of that metal which creates that colour. Strontium for red, barium for green, copper for blue, and we don't bother too much with sodium because sodium atoms produce yellow flames anyway. In fact, sodium is everywhere and it's difficult to get rid of it, basically. And then we add chlorine to it as best we can so that we produce a chloride. Now, in that flame that you see, there, let's say it's red and it's strontium chloride. The strontium chloride in that flame, and it's not a stable molecule, it only exists in that flame. And what is happening, according to the theory, is that the atom is, as all the electrons on the outside get more and more excited as it gets hotter and temperature goes up and more, and then they throw out a lumen of light, and in that case with strontium it's red light. And so that's really what colours are primarily doing. So if, for instance, then, we were going to make, say, red, then we have to obviously produce those particular chemicals I've been mentioning. And in here, I've just got 4 little bits of coloured material from typical fireworks. And in 1 or 2 cases, I'm going to add something on the base as well and show you what can happen. So let's take a little bit of stuff here, first of all, and let's then take what is a red, part of a red firework, like you saw on that rail there. And you see, I'm sorry, I picked the wrong one up. That's yellow. Never forget that. Let me find the red one. Yes, that's the red one. Now you see, that is a normal red, and you might even describe it as even pink. But look at that. Sorry. Now what you've done really, in that particular case, this is a bit complicated, you've actually used there the normal sort of things we use. But here we've taken the potassium out of it and replaced it with ammonium compounds. And so you get a deeper red because potassium is purple and colours the red in a slightly different way. So here we go, say, with green. So that's barium producing that kind of flame. And here is blue, but I'm going to show you another blue as well, because blue is very difficult to make. It tends to look white at a distance in the modern way that we use it. So we'll have a go with that one. So let's have a look at this blue to start with. And look at that blue. See, they're tending to show a kind of whitish sort of colour with blue, and particularly in this atmosphere. In the dark, you probably find that it looked a better blue, and you probably also find that if you put green with it, you will be deceived into thinking that it is in fact a better blue. Or if you were to mix, say, blue and red, then of course you would get a kind of violet. But in this kind of situation, these colours are not as good as they are in the dark, because fireworks are like people, really. Distance lends enchantment. I want also to, I'm coming very much to the end of the lecture, I wanted also to show you that we can actually make coloured flames without either perchlorates or even gunpowder. And here's a good example of this. We use, quite commonly, we use nitrocellulose in fireworks. And in this particular case, we are getting a flame, which we originally made these for a play in London where they wanted to have a distress flare in the flame, in the play for some reason. And so that's nitrocellulose burning with a bit of strontium carbonate. Nitrocellulose is a very cool burning. I'm not going to hold my hand in it, but you can see it's not particularly hot. And it doesn't produce any noticeable smoke, though in fact it's probably producing nitrogen dioxide, so not a word to the health and safety. So you can see that it's, and it burns a long time and is really quite effective. And I will come back to that in just a minute before I finish. So those are nitrocellulose colours. And I wanted to also show you a real freak. We don't know how it came about, but years ago, probably 19th century, a chemist discovered, really, that the pitch of a special kind from a special process in making beaten naphtha, he found that if that pitch was burned and nitrated properly, it would produce this quite extraordinary effect. And it's unique, and you'll probably never see it again because it's not obtainable anymore. So that really is a special kind of pitch which has been mixed with linseed oil and nitrocellulose and then nitrated with fuming nitric acid, which is not, it's somewhere between fuming nitric and bench concentrated, and then you will, if you use the right proportions and do it properly, you will get that kind of effect. I don't think you'll see anything quite like it. I've got still a bit left, and I jealously guard it, really, for doing these lectures. But that really is almost the end of the lecture. And so on this theme of indoor fireworks, I just wanted to show you, to finish, one thing. These fountains that I'm showing you now with nitrocellulose, of course, you buy in the shops in order to, and that's terrible. When I do the lecture in some of the colleges and things, they all come and pick that up, and they take it about 10 yards and then leave it in the corridor on the floor, everywhere. So, not very nice. Alistair, can I have the basket, please? So, really, as we're almost finished, I'll finish with this particular little illustration, very useful in church on Christmas or Easter. So here's an indoor thing for you. That smoke isn't the nitrocellulose, that is in fact the titanium that's burning, and probably other things as well. Just quite impressive at Christmas Day for children and church, actually. So, and the theme, of course, was light. So let me finish by saying that when Mark Lancaster went to the business school, I said we need a company statement, remission statement for Kimbolton Fireworks, and they came up with unrivaled in quality and service. And I see that the local garden centres decided to use it as well. And they said, you must have also had one in mind. I said, mine's a very old one. It's from my childhood Latin, ex luce lucellum, which I translate as out of light, a little profit. Thank you very much.
Well, Ron, I think that round of applause probably says it all. Thank you ever so much for coming tonight. It's my privilege now, as I said, we have the RSC with us tonight. It's my privilege to welcome their Chief Executive, Dr. Robert Parker, who's going to come and propose a vote of thanks to Ron. Dr. Parker.
Good evening, Ron. Good evening, everybody. It's very good to be here. Thank you for having us here this evening. And thank you for that really inspirational talk. As Alistair said, I'm the Chief Executive of the Royal Society of Chemistry. I don't want to keep you from the big fireworks outside too long, but I just wanted to introduce the RSC for a couple of minutes. We're a global organisation with the aim of advancing the chemical sciences. We haven't been around as long as gunpowder, but we've been around since 1841, when 20 gentlemen met in the Strand to become the Chemical Society of London. They would talk about chemical research and share their findings. Now, over 170 years later, we still have members, but we have 48,000 of them now all around the world. And they still share the latest research, and last year we published 25,000 scientific articles sharing research around the world. We talk to governments here and abroad to try and make sure laws and policies are based on good scientific evidence. And also we talk about things like risk and hazard and precaution. As Ron mentioned, sometimes people take precaution too carefully. We also talk to students and teachers like yourselves. We want everybody to enjoy the creativity, the fascination and the wonder of chemistry, as you've seen this evening. Learning about what everything is made of, how it works and why it works, just like the fireworks and the chemical reactions you've seen this evening. We do an amazing range of things to share this through resources for students and teachers, information, videos, games, to help anyone who wants to learn about chemistry learn about chemistry. We also share places where really significant parts of chemical history have happened, like here today. And I'm delighted to announce that today we are designating Kimbolton School as an RSC Chemical Landmark to recognise its importance and impact in the history of chemistry. We set up the Chemical Landmark scheme to officially recognise these important places. We award about 4 every year, and previous plaques have recognised the first ever man-made dye called Movine, the discovery of the structure of DNA, and even the real inventor of the light bulb, which many people would say was Thomas Edison, but it wasn't. It was Sunderland chemist called Joseph Swan. So today we recognise another great place in the history of the chemical sciences. The Reverend Ron Lancaster, a fellow of the RSC and master blaster pastor for 50 years, a true innovator in pyrotechnics and a great example of UK business success. Kimbolton recently put on incredible displays for the Queen's Diamond Jubilee and the London 2012 Olympic ceremonies. We're very proud to feature Ron as part of our 175 Faces of Chemistry, which celebrates the diversity and excellence in the chemical sciences in the lead up to the RSC's 175th anniversary. And we're equally proud to present this Chemical Landmark plaque recognising Ron's and Kimbolton Fireworks' contribution to business, to chemistry and to inspiration. Thank you. I will ask you to unveil the plaque now.
Well, I don't know what to say. I've said so much already, but this is really quite incredible, and I am most grateful to you for this, and really is, that really is something. And I don't think I really ought to say anymore, but thank you, that's wonderful. Thank you very much.